In this lesson, we're going to talk about the ideal gas law, which you may be happy to know is the last gas law that we're going to talk about. The ideal gas law is a combination of Avogadro's law and the combined gas law. So Avogadro's law told us that volume was directly proportional to the number of moles. So that symbol there is the symbol for proportional. And the combined gas law was that volume is directly proportional to temperature, but inversely proportional to pressure. So you can put those together and get that the volume is proportional to moles and temperature and inversely proportional to pressure. So whenever you have a proportionality, you can remove the proportionality sign and change it to an equals by introducing a proportionality constant, so some number that makes them equal. So we can now write it as volume is equal to R, which is our constant, times NT over P. And you can rearrange that to solve for R. So this constant is equal to PV over NT. And R is known as the universal gas constant. And the value of R is 8.314 kilopascal liters per mole Kelvin. Okay, so lots of units there. And so that's a value that you'll use for all your calculations, that value of R, and you'll be provided with that number. So that value of R came from having 1 mole of a gas at STP. So STP, the pressure is 101.3 kilopascals, the temperature 273.15 Kelvin. We had 1 mole of gas, 1.00 moles. And we know that the volume of 1 mole of a gas at STP is 22.4 liters. So when we use all those numbers and solve for R, we get that 8.314 kilopascal liters per mole Kelvin. In this calculation, we don't have the 4 because the numbers in the calculation aren't as exact as they could be. But that's where that number comes from. And so you'll use the value 8.314 kilopascal liters per mole Kelvin in your calculations. So what the ideal gas law allows you to do is calculate the pressure, the volume, the temperature, or the moles for any gas if you've got 3 out of the 4 conditions. So whereas with the combined gas law and the other gas laws, you had to have a gas that was changing conditions in order to calculate anything, with the ideal gas law, you don't have to have a change in conditions. You just need to know that information about that gas. Normally, we write the ideal gas law as PV equals nRT. And when it's written this way, it makes it a lot easier to isolate any of the variables by just dividing them on the other side of the equal sign. So that's the ideal gas law, PV equals nRT. So when you're using that ideal gas law in your calculations and you're using the value 8.314 for R, you have to make sure that your units match those that went with 8.314. So your pressure has to be in kilopascals. Your volume must be in liters. Amounts must be in moles, not masses, right? So you may need to convert mass to moles. And as usual, the temperature must be in Kelvin. So let's look at a sample problem. Use the ideal gas law to calculate the molar volume of a gas at SATP, which is 298 Kelvin and 100 kilopascals. So remember that the molar volume, right, that's what you're being asked to calculate, is the volume of 1 mole of a gas. So what givens do we have here? We have a temperature of 298 Kelvin. We have a pressure of 100 kilopascals. We have 1 mole, right? We're trying to find the molar volume. So we're going to say, well, we've got 1 mole. So what is its volume? And we're trying to find the volume. And there we have our R, our constant. So then we're just going to use the ideal gas law, PV equals nRT. We're trying to find V. So we rearrange that to isolate V. it is equal to nRT divided by P. And you just substitute in all the values. When you do carry all the units in your calculation, you'll notice moles will cancel, kilopascals will cancel, Kelvin will cancel, and you're left with liters, which is what you want because you're trying to find volume. So when you do that, you get an answer of 24.8 liters, which you might recognize because in our lesson on molar volume, we talked about the fact that the molar volume of any gas at SATP is 24.8 liters. So this is another way that we can calculate that number. So let's look at another sample. Find the temperature in degrees Celsius of 48 grams of neon that occupies a volume of 56.5 liters at a pressure of 1.20 atmospheres. So what have we been given? We have a mass of 48 grams. We have a volume of 56.5 liters, a pressure of 1.20 atmospheres, and we want to find a temperature. So our volume's in the right unit, but we don't want grams, right? We want moles instead. And for pressure, we need kilopascals. So first thing we're going to do is we're going to find the number of moles from the mass using the molar mass of neon. So there's that calculation where you divide by the molar mass of neon to get 2.37859 moles of neon in this situation. Then we need to convert the pressure to kilopascals. We can do that with the fact that we know that 101.3 kilopascals is the same as 1 atmosphere. So 1.20 atmospheres is 121.56 kilopascals. So now that we have those pieces of information, we can now use the ideal gas law to determine the temperature. So PV equals nRT. I'm going to rearrange that to solve for T. Substitute in all those values with their units. So 121.56 times 56.5 divided by 2.37859 moles divided by 8.314. All the units cancel except for Kelvin, the temperature unit. So that's what we've got, 347.3 Kelvin. We want to convert that to degrees Celsius, so we subtract 273 to get a final answer of 74 degrees Celsius. So we've been talking about the ideal gas law. So let's just refresh our memory on what the characteristics of an ideal gas were. So in an ideal gas, the gas molecules have zero volume of their own. The molecules have no attractive forces between each other or with their container. The gas molecules move randomly in all directions in straight lines. And the collisions are perfectly elastic, which means they don't use up any energy. However, that's the ideal situation. In a real gas, the molecules do have volume. It might be a ridiculously small volume, but they do have volume. They also do have some attraction to each other. Again, it's very weak, but it is there. Okay, they're not necessarily going to move in straight lines, depending on their environment and what might also be affecting their movement. And the collisions are not going to be completely elastic. So a real gas behaves differently than an ideal gas. But at STP, most real gases behave like an ideal gas. The problem comes when you have high pressures or low temperatures. Then they're not going to behave ideally. So why would that be? So if we think about what happens when a gas is at high pressure. So when a gas is at high pressure, its volume decreases, right? And when a gas is at low temperature, its volume also decreases. So at high pressures or low temperatures, gases have really small volumes. And so when they have a small volume, the gas molecules are closer together. And so when they're closer together, they're going to interact more. They're going to have more attraction for each other. Their volume is going to be more important because they're closer together and there's less space between them. So at high pressures and low temperatures, gases are not going to behave ideally. So when you need more accuracy in those types of situations, the ideal gas law can be adapted to reflect the behavior of real gases. However, you will be happy to know that you're not going to have to do that.